I have, oh, tomorrow's a long one, but I'll get you that spreadsheet. Then, I was thinking Thursday or Friday. I think what we have to do is just see how these lessons go. And if they really start dragging on us, maybe we'll say, okay, we'll slow down just a little bit. But if they don't, I just soon keep ourselves moving along. Because this lesson here, 3.7, is composition of functions. And you guys did that last year. And, you know, I figured that you were pretty successful. And then if I look forward with you, then Friday maybe inverses. And I think Monday, that'd be review. And that's because we've done inverses before, but we'll see. I might have to slow down. And if I do so, then the Wednesday test will be, oh no, it's a Thursday test. But I think I have it, yeah, Tuesday. I think I have it scheduled in such a way it doesn't matter. This test is going to be here even if we do slow down. I don't want to put, because otherwise it goes into the next week. And then we go to sign. Cosine. Then we begin trig. We'll do trig right up till Christmas and maybe a little longer.
Did we do some of that last year, or was that just physics?
No, we didn't do. You didn't do trig last year.
We did a little.
You did a little bit of sine and cosine relationships.
And it was like the sine wave and the sine circle.
You didn't do the unit circle and identities.
We didn't go far into it.
Yeah. Yeah, you looked at some relationships. We will go further. We'll get into a lot more stuff that is provable instead of observable. So, okay.
Have we done radians?
Have I used the word radian with you yet? I don't know. Can't remember. I'm not sure. Have I? Did we measure radians last year?
Oh, no, that was.
Yeah. So you'll get it with me this year. All right, let's take a look at this. So here's what we've done. First function we looked at was x cubed plus 3x squared minus 4x. And that was, let's just do this. That was the red function there. So we took a look at when we then multiplied the entire function by a value. When we multiply the entire function, we get a vertical change. So what this really is you could think of it like a k value, but that k value, if we put it with the y, would be the denominator. So, are you tuned in with me?
Yeah, I have it.
Oh, you look at that. Okay. So if you rewrote that, here's what I might do. I might say that that's y divided by 3 is equal to that polynomial. So I go and put that on the board. There it is, written on the board. Now, if we think of that 3 as a k, we can now say, when we divide by k, that k value ends up being a vertical shift. When you divide by 3, you multiply and you make it 3 times higher or lower. When you divide by k, you make it k times as far away from the x-axis. So what started here as just being at, what is this? Are these 4s? No, these are 5s. What ended up here is being something to the nature of 14. No.
Yeah.
Yeah, 14 becomes 38, or 14 times 3, 42. So this must not be quite 14. This is probably 13 becomes 39, something like that. So k, what k will do when we're dividing like that, when we take the y divided by k, it makes the distance that the graph is away from the x-axis k times as far.
do we get superscript?
Caret, like the up caret, shift six.
Oh, okay.
Yeah, up,
Thank you.
up shift. Okay, so now, I think what I did with, yeah, that's what I did with this. I made B a slider. So here we just make it twice as far. So then if you look at this low point on the graph, it becomes twice as far away from the x-axis. So your y values, when you divide by k in the equation on the graph, you multiply. So just like when we did horizontal shifts in slides, when we would like add to x horizontally, the equation would be subtracting x, subtracting from x. So like h. So if you added h, the equation would have to subtract h. So the graph moves opposite of the function, or opposite of the operation. Okay, so now let's look at the parent function again, or the original function. Oh shoot, what happened there? Oh, I made. Okay, let's see, let's turn this guy off. So now we look at our original function here, and then we're going to look at what happens when we change the x values. So right now I just have it divided by 1. So this is still, this f4 is the same as f sub 1. But then if we, for example, if we have the x value, what we end up doing is we spread out the graph. So in other words, we have to get 2 times as far away from the y-axis to get the same output value. And that's what we went over on Friday. So let's take this to another graph. Do you guys know the equation for a circle? It's the equation of a circle. X squared plus y squared is equal to radius squared. That's the equation. What's that?
You're thinking of that same thing, but it's minus h and then a.
Yeah, you're thinking about how to put it into a graphing calculator? Yeah, I'm not worried about putting it into a graphing calculator. That's just a cheating way of getting around this right in 2 parts. You don't want to have it turned like this?
No, it blocks it, like, it catches the glare that way. I can see it.
Oh, it catches the glare? Okay.
Yeah, I can see it.
Because it's hard for me to hear through that thing.
Oh, sorry.
It's all right. So this is the general form of an equation for a circle. So if we had a radius of 5, that would be 25. And then x squared plus y squared would be all of the points of the circle with a radius of 5. So that's what I have here. Here's the equation, x squared plus y squared is 25. And we have a circle of radius 5. So what if we wanted to get this circle to be moved out here? Get it twice as far away from the y-axis. So in other words, if I wanted to take this point here, the origin, and move it over so that the origin is here. And then at the same time, take every single point on the circle and move it 5 to the right. So then I would also take this point here and make it into the origin. How do we move the entire circle over to the right?
Would we add 5 to 25? Or no, could I just make it a bigger circle? Yeah, would we add it to the other side? Okay.
Well, let's take this point on the circle, which is what, 5, 0? So 5 comma 0. That's the x and the y. And what we want to make it turn into, we want to map it to 10, 0. So does the y change? No, the y does not change. Does the x change? It becomes
What's this big?
twice as big.
So multiply it by two.
So you can multiply
Multiply
it.
it by k.
Well, but we're not gonna multiply it by 2. Let's go back. Shoot, now I gotta look at all those lines. Can we look through those lines? Yes? Okay, so let's take a look at with the slider here again, what happened. With this slider, this was supposed to be a slider. As it gets bigger and bigger, and that's the number I'm dividing by, the graph moves further and further away from the y-axis. So if I want to take, and I want to just shift this circle and move it over, then I'm going to be, if we're just going to slide it to the right, I'm not going to be dividing by this, because what's going to end up happening is it'll do this if I divide. Everything will get further and further away. It'll turn into an oval. But if all I'm doing is I'm shifting it, sliding it to the right, you think of it this way. If I'm adding 5 to the x value on the graph, this ends up being h. In the general form, we have to subtract h. So here's what I want to do. I want to add 5 to this h value, so now it's x minus 5, and my graph just shifted over to the right 5 places. If we, oops, here's my slider. If we move it only 2, the graph moves to the right. So the greater h becomes, the further it moves to the right, but that has to happen by subtracting. So if, for example, in this equation, which is x minus h, quantity squared, plus, and we're only dealing with a horizontal change, so we can do this. If I still need to have, because y is 0, and I still need to have this value here equal 25, and I am starting with an x value of 10, what do I need to subtract from 10 so that when I square it, it equals 25?
-15. Oh, no.
5. You subtract 5 from 10, and then you have 5 times 5 is 25. That gets you this point out here. Take a minute and look at that. Come up with a question for me. Do you follow what I'm trying to explain with these lines and scribbling? You see, when we were evaluating initially, we had 5 squared plus 0 squared, which was 5, 0, was equal to 25. And that would be this original point out here on the blue 5, 0. But now I want to say I want to move this thing out here to the right, so I'm going to add 5 to the graph to get to 10. So I go out here and I say, well, there, now it's 10. But how do I still get 0 so that this point stays on the x-axis? I have to subtract 5, because 5 times 5 is 25. So 5 squared is 25. What else is 25?
Negative, or Negative 5.
So negative 5 squared is equal to 25 also. So if we took this point here, which is a negative 5, what do we subtract? So when we square it, we get 25 again?
0. Or you can subtract 0 or negative 10.
If I subtract 0, then I move this point to here. You could, if you had a negative 10, that would mean then you would end up starting out here, but we start here.
Well, subtracting negative 10 is the same as adding positive 10, which would get you a positive 5.
Right. So if you subtracted a negative 10, then you would, in essence, be thinking about moving it in the other direction. And that would be taking this point and moving it here, and taking that point and moving it.
But the answer is positive.
I'm confused for sure. Earlier you said it would move negative 5 to the center point, but it wouldn't move it over, it would just move the center point of the circle. So if you subtracted 0, it wouldn't move the point over, because it's still 0, 0. The origin still was 20 of it. I'm confused.
Say that again.
So you said if we subtracted 0, it would move that point at negative 5 over to 0, but it wouldn't, because it moves the circle from the center, its origin, like the center point, so the circle would move, right? Because it would just say 0. You said it would take the outermost point there and move it over, but it wouldn't, if you subtracted 0.
If you subtracted 0, it wouldn't move.
Yeah. But you said, I thought you said it did.
No. If you
Okay.
subtract,
I just misheard you then.
yeah, okay, no, it's gonna move.
Well, not if you subtract 0, it won't.
Right. Yes, that's true. But your idea, if you take negative 5, subtract negative 10, that'd be like negative 5 plus 10. So that, a negative 10 would be a shift to the right 10 units.
What?
Oh, you're right, yeah, it'd be, excuse me, you're right, it'd be a shift to the left 10 units, so this point would move to here. The negative 5 would move to negative 15. So I don't know that you can put, if you put negative 10 in there, you would be moving it to the left 10 places. So the point negative 5 would then move to negative 15. Isn't that right? No, it moved to positive. Oh gosh, now we're talking double negatives. So if you subtract a negative 10, the negative 10 would be the shift to the left. I got myself confused. Yeah, I know it is. Okay, negative 5, subtract the negative 10. So this would be like a negative 5 minus h, which would be like x minus h. And then h would be equal to negative 10, which would be the shift to the right. Oh, I'm sorry, the shift to the left on the graph. So if you did that, the negative 5, that would become a positive 5 squared, which is 25. Yeah, so that's just simply gonna be a shift to the left, but not to the left 10. It would be to the left 10, because you would come out to negative 15 is where you would end up. See? You see it? It just moved it. Are you looking at it? So if you put negative 10 in there, this shifts to the left negative 10, and the outside edge of the circle is at a negative 15.
Why is that? It's being squared. So would a
So
negative?
negative 15, because it's not that negative 15 is squared. And it's not that, and the only reason that 5 is squared and negative 5 is squared in the original function lines up at 0 is because the shift hasn't occurred. So if we put a negative 10 in here, then this here squared is equal to 25.
Yes.
But the shift of the point goes from negative 5, 0 to negative 15, 0, because this is a movement of 10 in a negative direction, which is our h value.
Right, because the radius doesn't change.
Okay, good.
Okay.
So make sure I'm not teaching you any gibberish. Yes, the
Right.
radius doesn't change.
That 25 is always going to be 25.
Oh, there-
if it's
there's-
the same circle.
See how this gets twisted?
Where do both of them?
Do you see how it gets twisted? Did you just nod your eyes? Yeah. Go ask those guys that are down with John right now. What twisted you up the most last year? This is it right here. Sometimes we had some long, hard discussions after quizzes and tests. So here we are. This is what happens when you add and subtract to the x value. You move things left and right. And when you add and subtract to the y value, you move things up and down. But then when you multiply, I'm gonna hide this guy. Oops, that's not what I wanted. What happened here?
I think you pressed, like,
There. So, oh. Okay. So when I multiply, I gotta do this. Oh shoot. I'm gonna use a and then here I'm going to use B. Okay, now watch what happens here when we multiply by A. So when we multiply by A, we are saying we're going to make it this many times further or nearer the y-axis. So when we multiply by A, we squeeze it in. When we divide by A, oops, I want this thing to go from 0 to, let's just say, 5. So in this case here, if it's, okay, when it is small values, less than 1 and greater than 0, it stretches things out wider, which is the same as dividing. So like if I had x over a, x divided by a, that's the same as multiplying by like 0.5, for example. 0.5 would be the same as dividing by 2.
How could that be raised squared?
What's that?
I mean, it's, y squared plus x squared is r squared.
Yeah, why is it?
Well, when you shift it like that, is that still true?
Sure. Oh, it totally holds true.
The radius is getting bigger than x
The radius is remaining the same. Within the circle, it remains the same. Oh gosh. Okay, you ready? Okay, so here's what I did. I made my x-axis twice as big, right? Are we ready for this?
Okay, fine.
Yeah. So here's what I've done.
No way. That's not good. I see what
Okay, now, here is the original. Four along the x-axis, agreed?
you're
8 along the x-axis, agreed? A squared plus b squared equals c squared. Those are Pythagorean triples right now. So 3 is here. So 4 squared is 16, plus 9 is
23.
16 plus 9 is 25. The square root of 25 is 5. Okay, 8 squared is 64 plus 9 is 75. This hypotenuse is root 75, which is 5 root 3. Golly, what crap that is. So it's 5 root 3 is what it is. 5 times the square root of 3. Not, yeah, it's close. Yeah, it's 5, it's 8 and 3. So as we go around this circle, what we have is an infinite application of Pythagoreans on right triangles. That's what a circle is. Are you sticking with me? Or are you just laughing at my expressions? This is a huge idea and concept. But if I'm going to double my x, I'm going to stay on that shape, but it won't be a circle anymore. But if I double both my x and my y, come on,
Oh, there it goes.
did it go?
Yeah.
Yeah. I'd say that the computer is probably getting a little, where this thing happens. Okay, so now if I double my x and my y, I gotta go down to my b's. Now take a look at what's happened. If I go and I find, for example, one triangle, all I've done is I've doubled the length of that leg, and I've doubled the length of this leg, therefore I have to double the length of my hypotenuse. That's like this idea of having a 3, 4, 5 triangle, and then turning it into a 6, 8, 10. So 2, 4, here's 4, here's 3, here's 5, here's 8, here's 6, there's 10. That's where this equation comes from. It comes from the Pythagorean. Yeah, a squared plus b squared equals c squared. This is the Pythagorean. It's the distance formula. We just put it on the grid.
That's cool.
You think it's cool, huh?
Yeah.
It is. It's awesome.
Really cool. Let's see what I I understand what you did. I still don't know how it works.
Well, it works because the Pythagorean holds true for all right triangles. And all we are doing there is we are extending a triangle from a point on one circle to the point that it maps to on the other circle, if we go twice as far out and twice as high up. And it works very nicely because these circles have a center of 0, so we do all of our measuring from 0. You know, we're just going to measure, this is for, oh shoot, let's get rid of this junk. See what I'm going to do. This is 4, this is 3, here's 4, here's 3, that's got to be 5, right? 3, 4, 5. Go twice as far. Okay, instead of 4, we're going to go to 8. And instead of going up 3, we're going to go up 2, 4, 6. So now we're 10 away. And we can keep doing that. You go further and further away and just make this circle bigger and bigger and bigger. And this is how much we're multiplying our legs by. The reciprocal of this. To get mapped like that. It's very cool. This is the foundation of trigonometry. Right here. You can't understand trig without understanding a little bit about circles and where the formula of the circle comes from. Because then we tag onto this, we call these lengths of this triangle something different. We call them cosine and sine. And then we don't use complex radii, we use a radius of 1 to make the math easy. But then we can just multiply our distances out. So just like this, if I say, well, instead of going that far, I'm going to go twice as far, therefore I have to go twice as far along that line. Because it's a circle. This is the foundation of all math, man. Right here. At least as it goes higher and higher and higher. You know, I'm not talking about math, I'm like doing statistics work and stuff like that. I'm talking about like getting to the moon, coming up with, you know, what's a molecule's behavior going to be. All that stuff follows curves, nothing's straight. Euclidean is like, that's how we learn how to understand it, but then we have to put it on a curve. This is how we get to do it. We do beginnings of a circle. And then in nature, nothing's perfect either, except nature itself. The Earth isn't perfectly round. The planets don't go in a perfect circle. So then we have to modify. And we have to do things like, we make one of those not quite the same multiplier. And then it becomes a whole lot easier just to deal with 1/4 of this. You take all of our answers and know that they're 4 times the information. So yeah, that's what this is all going to boil down to. You should do some of these problems. Page 182, 1 through
Is that a
11.
recommendation?
Yeah, you should.
Suggestion?
This is where it starts becoming a lot more involved and I think a lot more cool. Is once we get here. And a lot of the cool stuff is coming. Next chapter gets really cool. And so much of the physics from last year is going to start making more sense. Next few weeks. And we've got chapter 4, chapter 5. That's all true. So under every scale change, the pre-image and the image are congruent. True or false? Are they the same size and shape?
Under what?
Under a scale change, under every scale change, are they always congruent? No. Some of them are. You know, when we had the circles multiplied when A and B were the same number. But they don't have to. We changed the shape of the graph. So the shape of the graph is what we say is either congruent or not congruent. So see what you can do with this stuff, bring it back so we can have some discussions tomorrow. I think it's 1 to 11, right?
Yeah.
Yeah. Try not to work backwards from what your graphic calculator does for you when they ask you to make predictions. Okay? And remember, when you add and subtract, you're sliding. When you multiply and divide, you're changing magnitude, size change. Go back to some of that basics that we did in geometry, where we multiplied ordered pairs and made it get bigger. Or we just added in these, it's the same thing. So, come in slowly, Galen Allen, you're new here, and I have no idea where I'm gonna put you, okay? I have no idea where I'm gonna plop you down. I might, she taps right there. We don't know. Did somebody sit there?
No.
Oh, okay, then tap away, you can sit there. We'll put you there. I have a screen, and
My ankles
what do I have? I have 1, 2, 3. So,
Dagan, Mr. Dagan, it's still videoing.
is it? Good.
We started watching your video in English.
Wait.